Here is a neuron. You should know the parts of the neuron. And then so far, we've already talked about the resting potential, the resting membrane potential that is present in a neuron at rest. This picture provides an overview of the different membrane potentials, meaning the changes in those millivolts that we'll see in different parts of the neuron. So what we're going to do in this video is start with graded potentials, which are also called local. Too big size. So local potentials are changes in membrane potential. They're going to happen locally. Graded means they can be different sizes, different strengths, and they're going to occur somewhere along the cell body prior to that axon hillock. We're then going to get into the action potential, which is that electrical signal that travels down the axon and causes synaptic activity, causes neurotransmitter release. Neurotransmitter release leads to activation or inhibition of another cell or neuron. At this point, we'll talk about graded potentials again. So graded potentials, remember, because this postsynaptic cell here is at rest at first. So it also has resting potential. And then a stimulus to it can cause a graded potential. So we've already done resting potential. We're going to start here now, then do action potential, do the synapse, and with the synapse, we'll then bleed into the next neuron. So go back to graded potentials in the second neuron again. It's kind of an overview of really the rest of neural signaling. So what I want to start with here is have you think about a couple questions here related to some of these chemically gated and voltage gated channels that I talked about in a previous video. So in a resting neuron, so a neuron that's at the resting membrane potential, are the gated ion channels opened or closed? And then what happens? Well, so let's do that one first. They're closed, right? They're gated and at rest they're closed. And I've kind of got a hint here, right? So what happens if a sodium channel opens? This is a really good question. You should be able to answer it. What happens if you've got a neuron at rest and there is a sodium channel that opens? Is something going to happen? Yes. Sodium will flow into the cell down its electrochemical gradient. It's negative in here inside the cell. There is more sodium outside of the cell, a whole lot of sodium. So if this channel opens up, sodium is going to rush into the cell down its electrochemical gradient. That is a result of that membrane potential, that stored energy due to that was created by the sodium-potassium pump, largely. This is going to then, so opening a channel can create a signal. And this is what it means for membranes to be excitable. Can you open up channels like this to cause a change in membrane potential? All cells have a negative resting membrane potential, but only excitable cells, so muscle and neurons, are excitable, meaning they can rapidly change in membrane potential. And that is due to special proteins that can open up and then propagate this signal down the axon. So voltage gated channels are going to be important for that propagation down the axon or within a muscle cell even. What happens? Oh, so let me bring up the answer here. Sodium flows down its electrochemical gradient. When sodium flows down its electrochemical gradient, sodium rushes into the cell. What happens to the membrane potential when that happens? To answer this, we're going to draw a graph of millivolts over time. Get comfortable doing this. Millivolts over time. And if we have a place where the sodium channel opens, let's say right here we're at rest. What is rest? Minus 70. If a sodium channel opens inside the cell, it's going to become, okay, sodium's flowing in, positive ion is flowing in, that cell inside of it is going to get less negative. Less negative. I'm just drawing a random amount up there. Don't care how big that blip is right now. The point is it's becoming less negative. What is this called? This is called depolarize. Becomes less polar. This terminology is not wonderful. The cell is polarized, very negative inside, positive outside. It's becoming less negative, so it's depolarized. I'm just gonna, for reference, put 0 up here. And just to be really clear here, depolarize, that's referring to this part right here. And actually, what's happening after that depolarization is called repolarization. The cell is becoming repolarized. It is polarizing again. So that terminology, get comfortable with it. We're going to see it and more. Okay. Next, we're going to talk about the initiation of one of these local potentials. Local meaning not down the entire axon, just within the cell body or dendrites. So something has to stimulate this. That stimulus is going to open up some ion channels, open up gated ion channels, either chemically gated or mechanically gated. This is like a touch receptor in the skin. We're going to be using chemically gated as an example. Yeah, so here's actually a diagram that I drew a similar thing for you at the end of a previous video where I labeled on a neuron where the chemically gated ion channels are, where the voltage gated ion channels are, and all the different types that you need to know about. So what I want to do now is start here. Start with a stimulus. A stimulus is going to open a gated ion channel, and that's going to initiate the action potential. Not every time, but potentially. So let's zoom in to a little piece to the dendrite here. Let's see what is located here. Well, I've already told you, right? Chemically gated ion channels are located there. Let's look at those. You know what those look like, right? They are closed because they're gated, and they've got a spot for some chemical to bind them. That chemical could be a neurotransmitter. It could be another circulating chemical messenger. Here, I'm just going to give you an example. You may have heard of glutamate. We'll come back to glutamate, an excitatory neurotransmitter. So this chemical, glutamate, is going to bind. And when it binds, it's going to open up the ion channel. We know that, right? That's going to change the permeability of the membrane to whatever ion this channel allows through. So let's say this is a sodium channel here that glutamate binds to. So again, sodium is going to rush into the cell once that membrane protein opens. What's going to happen to the membrane potential again? Could we graph that? Let's do it. Okay, on here, what I'd like you to do is graph the membrane potential changes during a local potential. So this graph here is similar to what I drew on that previous slide over time on the x-axis, membrane potential on the y-axis. And I've got some different stimuli here, or a removal of stimuli that I'd like you to pay attention to. So what we're going to do is draw a graph showing the changes in membrane potential. That means up, down, over time, due to the movement of the ion flow over time, which is due to whatever I'm telling you happens up here. So if a chemical stimulus opens gated ion channels, for example, glutamate, we're here at rest, what's going to happen? Depolarize. When it's removed, repolarize. What happens if we open potassium channels? Wait a minute. Okay, there's high potassium inside the cell, but it's also negative inside the cell. So the electrical gradient, we gotta draw this. High potassium. The electrical gradient is actually in, but the chemical gradient is out. And I'm just going to tell you this, that the chemical gradient is larger when we're talking about -70. Potassium will actually keep flowing out of the cell until the membrane potential reaches about -90. That's the point at which the two balance out. So when we open up potassium channels, potassium is going to rush out of the cell. That's going to make the cell membrane become more negative. We have positive things leaving the cell until the stimulus is removed. Now, if I wanted you to label, oops, what I want to do is just erase this. If I want you to label what these terms are called, let me just bring this up here. So we've already done this: opening of a sodium channel, then closing; opening of a potassium channel, then closing. You've done that. Could you label where this cell is hyperpolarized, depolarized, and repolarizing? Hope you can. So here we've got a depolarize. Here we've got a hyperpolarize. What does hyperpolarize mean? It means really polar. It's more polar than it was before. Yes, I got that. And then we have a repolarize as we're going back negative again. Going back towards rest. So anything going back towards resting membrane potential is repolarizing. Okay, so local potentials. These are both examples of local potentials. Blips, changes in membrane potential, not yet an action potential. That distinction will become clear later. Local potentials can either be depolarizing or hyperpolarizing. They can make the inside of the cell either more negative or more positive, depending on what? Depending on what kind of channels open, right? Because the channel that opens is going to determine what ion is able to go through. Different ions move through in different directions. I'll tell you right now, calcium and chloride are two other ions that can move and will move through differently. So I believe here I've got the same thing I just drew, but kind of a nicer schematic of it, so you can kind of see the same thing I just showed. And what's happening here is something that is causing that channel to open. Here we've got that chemical that is binding, chemical stimulus. Once it's bound, causes the ions to flow in. When those ions flow in, the inside of the cell becomes less negative. So this is a schematic of what's happening with the membrane proteins. Likewise, here we've got what happened with potassium channels. Notice this return to resting potential isn't typically called repolarization. Repolarization is typically referred to as becoming negative again. So depolarization, repolarization kind of go together. In this scenario here, we've also got ion channels that were present. This ligand-gated ion channel is a potassium channel. When potassium opens, channels open, potassium is going to flow out. So this is making the cell more negative. Okay.